Great. So hopefully this will feel familiar, and hopefully we'll clear up some questions or confusion from before. Another thought-provoking question for hope is, so here's a list, and like this is again, is this sorted? No. It's not your question. Like, it's not sorted. Why is it not sorted? Because this intuitively, like this 5 should sort of be over here. And then is this sorted? Oh, someone's trying to break in. So is this list sorted? No. No. But now here's a weird question, and no right answer. Wrong answer. Yeah, that's the best answer. There's no wrong answer. Which one is more sorted? So neither of them are sorted, but one seems more sorted than the other. The one on top? Yeah, so could you guys sort of articulate why you feel that?
Well, I see that there are 2 pair of numbers that go consecutively, like 1 and 2, and 3 and 4.
Yeah, I think for the top, you might just need 3 steps to sort it.
Yeah, so you can talk about like, okay, there's like sorted subsequences, or that like how many things do we have to move in like a perfect world if we want to spend as much time thinking about how many actual moves it. And either way, like this one seems like more almost sorted than this one. And there are a few ways of kind of measuring how sorted. But I just want to introduce this idea that, and then it isn't like there's the one right way of measuring how sorted things are. There's one that's really popular. What I'm talking about, I just want to plant a seed in everyone's mind that like, hey, this is, like we can sort of approximately get closer and closer to sorting. So that, or to a fully sorted list. So that idea, do we remember kind of a high-level description of quicksort?
It's like you need like a point or something, a pivot or something like that?
Yes, so there's a pivot.
Yeah.
Let me. This is a weird implementation. So here's a Pythonish. We have some array implementation. And in an intuitive way, we can say, all right, here's 5, 3, 1, 4, 2. And what we can do is we might say, let's choose a pivot. Let's choose this as our pivot. And why did I choose this there? Usually it's either like the first element or the last element or exactly the middle element or something. You just pick one way and stick with it. And then you say, okay, I'm going to transform, I'm not going to sort it, I'm going to partition it, is the word, around that pivot. And what the result of partitioning being is something like this. 2, 1, 5, 3, 4. It might not quite be like this, but this would be a legal partition. And what that means is that, sorry, to make it a little clearer. We got 1. What that means is here's our pivot, and we've simply taken everything that's smaller than our pivot and put it on its left, and everything that's bigger than our pivot and put it on its right. And that way it's sort of, in some ways it's more sorted than it was before. So we're getting close. And what's neat about it is that, if you kind of imagine what would this look like actually sorted. So we're not there yet, but we want to get from here to 1, 2, 3, 4, 5. Right, and that's the sort. And once we've done this partitioning, we know that, well, this 3 might be in the wrong place, but it's on the correct side of the partition. So now we just need to think about quick sorting, finish sorting this chunk and finish sorting this chunk, and they can sort of ignore each other. So we've successfully sort of partitioned our array into 2 discrete chunks that are smaller that we can process. So now that intuition seems Is anyone suspicious about that intuition? Okay, so you all know how it works, okay? But and here's where so quick sort's often introduced also as like sort of a cool exercise in recursion. And so with that suggestive statement, how might we finish sorting this half and this half? Yes.
Pick the pivot to be the last one again of the stop array and repeat the step. Make sure that everything that's less than the pivot is on the, in this case, the left side, and everything that's greater than the pivot on the right side.
Okay, so yes, you're sort of jumping ahead. I like what you're saying, but you're saying, okay, let's kind of do it again on each half. And I would say, okay, yes, we want to recurse, we want to be recursive and call ourselves on this part of the array and part of the array. Was that like painfully boring for everyone here? Yes. Okay. So now I'm going to spell it out a little bit more detail, and then we can talk about that actually. So let's keep this now. But I wish I could move it. So at a high level, forget it. At a high level, quicksort is sort of deceptively easy to write, where you just have like your midpoint is the result of partitioning the array. The beginning is 0. Both keeping 0. There's the beginning, the end. So this is usually 0. This would be like the length of the array. And this is just because thinking ahead about the recursion we have to do. You'd have your new midpoint be the partition of array and the subsequence of the array we want to think about. And then we just do quick sort that array, beginning, midpoint, quick sort that array from the midpoint. So that's it. I say waving my hand. And what we might define elsewhere is like, okay, so we use quicksort by saying, oh, I want to sort my array A, I call quicksort A0 blank. That, or A dot size or A dot length. That's just to kickstart this, you have to give these initial values. And there's obviously, so this is implemented, right? These two lines are recursive, so we can just go right back to our quicksort. So we only need to implement partition. And I will tell you right now, like there's going to be an alpha in there. But partitioning so I gave you this sort of the intuitive description before. Do we feel that we can sort of implement this? Or was there any mystery here?
What was that again? Like when we separated the array into.
Yeah, oh, sorry. Yeah, so partition roughly would be the thing that we have 5, 2, 1, 3, 4, and we choose, this as our pivot, for instance. We want to end up with something that might look like 1, 3, 2, 1, 2, 1, 3, 4, 5. Here's our pivot. All these things are just small pivots to the left. These things are bigger or equal to right.
Well, let me confuse on what the return value of partition should be.
That's right. So the idea is that so let's say we partitioned this infinite here. So the initial quicksort call was array is this. And then B is 0 and E is 5. And then we call partition, and this would return 0, 1, 2. this would return m is equal to 3 because that's the index of the midpoint, like of the, that's where the partition element should have gone. And like, okay, just put it, if you just put a pin in that for 1 second, and then, because then we end up calling quick sort on the array from 0, and then that midpoint 3, and then quick sort array 3. And so that exactly captures that idea of, okay, we just want to sort this subsequence and this subsequence separate.
Oh,
So this M is saying, all right, let's cut it.
but we're never really cutting it. Like it's all,
Sorry, this,
we're never really cutting the array, separating
Yeah.
it physically. Kind of.
we're never making new arrays in this description. There's another question.
And isn't it 5 beyond the range of the array though? Wouldn't it be 4 because it starts at 0?
Yeah, so this is a convention, I guess, where, so I've been cheating by not actually implementing anything yet. But you might, this is, the length of the array. So when we're saying, okay, the actual elements are from 0 to 5 minus 1, so to speak. And then here it'll be 0 to 3 minus 1, and then 0 to 2. And so that's just sort of the convention we're using for this implementation. But yes, good catch, because I promise you, like, this whiteboard implementation will have an off by 1 error, at least one place. But there's that sort of thing. Those are good questions. Are there any others? Okay, so we can move on to continuing the actual implementation. I'm just going to be inclined. Check my notes first. Type. Yeah, confusion. Yeah. All right. Sorry, I'm just. Behind the scenes stuff. I almost had an invitation from the blog. I don't want to share work with them. So we're gonna have to wing this one a little bit.
It's okay, I have mine.
You have your, would you go for it?
I mean, it works, but
Yes?
yeah, this is like review for me.
Okay.
No,
If you don't want, like, can I steal your?
it's pretty much the same thing. I did it recursively. I had a partition. I call mine partition. It has a pivot. It has a low. It has a high, which is just I and J. So while we're iterating, we're looking at I and then I plus 1, which equals to J. So we're just looking at those, comparing them. I'm using whiles and I'm comparing and swapping. So if I is less than J, then I have a temporary and I'm just swapping between.
Yeah. So as a, if I try to wing this, we'll see. Let me know if there's a button. You can be the code reviewer.
Okay, thanks.
Oh, thank you. So, do people want to get started, or should they just see me learn about it?
But what is also in this inside here you have to define what the pivot point is, right?
Yes. So we might, for instance, say our pivot value will be array E minus 1. So that's the 5 versus 4 concern. I'm saying this will be the rightmost element. This one. And then, so we want, so like, kind of this as our guiding example. What do we want to do? In general, the approach would be to say, well, got to start somewhere. Let's start at the beginning of the array. And I'm just going off Wikipedia has a nice description where you want to maintain that loop invariant. So I mentioned those occasionally. All right. Tell you, okay, so here's, yeah, I think it's we'd have something like for J, and this is just Pythonese, but don't worry about it, I'll expand in a second, in range B to E small. And so what that's saying, this is just for J equal to B, J equals B, J is less than E minus 1, J plus plus. Like that, everyone's favorite for loop. This is just the Python way of saying it. What we want to do is we want to compare ARR sub J to our pivot.
So if it's less than it, less than the pivot value, we put it into,
To the left.
yeah. Right, yeah. But you need to erase that, right?
We'll need to kind of swap.
Yeah, so swapping through array, like we're all thinking the right things. You're wrong. Just, so what we can do, and this is a common enough way of thinking about this sort of, do you know the phrase in place? If I say let's modify the array in place.
Oh, it's like, yeah, like in out. Or correct.
In this case, it means like we're not going to basically we're not going to try to copy the array.
Right,
Modify
yeah.
the array. And so when thinking about like in this and other sorting algorithms, we usually want to do it in place because we don't want to copy the whole array. And so we can kind of start thinking about sub arrays, and that's where a lot of these, I guess, where this kind of weird notation is coming from. Other stuff like that. So we can think and saying, all right, I will be, so for the beginning, we could basically say, all right, I is going to be the subsequence. Yeah, no. We want to think about maintaining a loop invariant of some kind, where, for instance, let's have improvising, it's always a mistake. But I is going to be so we want the partition list for the right half is equal to or greater than the pivot. And the left half is smaller than the pivot. And so if we start I here, that's like defining this subsequence. And it is the pivot. So this whole subsequence of one element is greater than or equal to the pivot.
Equal.
Or sorry, in parentheses, greater than or equal to the pivot. As in like, oh, hooray, this is setting up a loop invariant thing. And then we can say, all right, we want J, which is going to start here, to always be the upper bound of this other subsequence. So right now, we have this empty sequence of elements that we know are smaller than the pivot. And there's sort of a lot of moving parts here, and I don't have to check.
Could you expand on the invariant?
Yeah, that'd be. The intuition that I'm trying to get here is that for Z from B to J, A sub Z is less. I'm going to erase this. A sub Z is less than the pivot. And then for Z from J to from I to E minus 1, A sub Z is greater than or equal to the pivot. These are comments. Actually, not Python comments, but whatever. And this is saying, this is what I want always to be true. So every time this loop starts and when it ends, this is always true. This is, I'm sort of setting up a lot of things and I haven't connected them yet. I hope to get there soon. So this is saying everything before J should be smaller than the pivot. Every iteration through this loop. So J is growing. So that's like, okay, every time we're going through this loop, we have to think, oh, by the time we get around here, we better have kept this true. And then occasionally we might be updating I as well. And when we update I, we want to keep this true. So these are our sort of guiding principles. So to make that a reality, so right now, for instance, this is sort of silly. I got I is D minus 1, and J is 0, because B is 0. So J points to here. So for Z from 0 to J is the empty sequence. Like there's nothing before J, right? So this is true. Right, so far so good. And from I, so this is including 4, so to speak, to the end, which is just this is greater than or equal to the pivot, because the pivot is 4.
Yeah.
Great. Now we're thinking ahead and saying, well, we know J is going to increase. Oh crap. What should we do? We want to maintain these. So we know, like, so first, if we don't do anything, what will happen? What will happen is that J, the next iteration around, J will have moved to here, and then we'll check this, and we'll say, okay, for 0 to J, so that includes 5, this 5 should be less than the pivot. And that's, okay, we're in trouble. But we would like to maintain that, so what can we do?
If it's less than the pivot's value, you have to add it to the subsequence that's to the left. Right.
Well, let's first focus.
Right. Like swap, sorry.
Yeah. Okay, so swapping is a good action, but this is bigger than the pivot, and that's what we're calling.
Yeah.
So,
so then you have to swap it so that it is basically after the pivot.
So it's somewhere else.
Yeah.
Yeah. So what we can do is we can say if. So this is what we're concerned about. If ARR, sub J is greater than our pivot, then we want to put this somewhere in this. Basically, we have some spare room in this mysterious I sequence. So what we can do is say, well, let's make some room. I equals I minus 1, and then swap ARRJ. Almost every language has some kind of swap thing. And if not, you will write a million of these in your time.
Will you pass the indices?
Yes. You'd be able to pass references and so on.
The array and the 2 indices.
I guess I don't like picture. T equals A sub I, A sub J, A sub I, equals A sub J, and then A sub J equals T. This is the swap. That's just something you'll see many, many times. And if you find yourself writing that, just see if maybe there's a small function you can call. Just because like everyone's seen this before, we're like, eventually everyone will see this in their programming career and get used to it. But like, it's a little worky. So in any case, what does this do?
Swaps I and J.
Yes, so
yeah.
now we're going back in time before we made that horrible mistake of not doing anything. Now we're doing something. We're saying, okay, J is 0, and ARRJ is bigger than our pivot. So what we do is we make this I sequence of things greater than or equal to our pivot bigger. We now say I points to here. I know that's already sort of an issue, but we're not not done yet. We swap the 3 and the 5. So now we've done 2 things. Actually, we've increased our I subsequence, this I, which started at the end, but now it's 1 earlier. Concretely, now it's 3 instead of 1. And implicitly, because we're in this for loop, J will jump over here. But now, we've maintained our loop invariance, because we've checked for loop. And that, yeah, I guess that's sort of the punchline. And we might, so right now we feel confident, hopefully, that hey, whenever we find an element that's sort of beyond our pivot, we know what to do with it. We can increase the room here, move it here, and maintain the loop there. What if the element, what if the element is less than our pivot, as it is here?
This is less than the to the left.
That's right. That's it.
If it's less than to the left, right?
Yeah, so we want it to be, if it's less than our pivot, we want it to be in this J subsequence.
Maybe we just let it be.
Yeah, so sort of both of you are right. Like we want it to be on left, but it's sort of already at our left, so actually we can be nice and relaxed on this now. Let it happen. And then, so okay, and then this can proceed narrowly. Are there any other challenges or things to be suspicious of? Or sorry, yeah. Else. This is actually quite fun. Pass means do nothing. It's a no, or it's a do nothing. So, can we get through this loop successfully? Like, is this loop done, I guess?
Well, it doesn't sort the left side. It just swaps with the,
So yes, this is just a partition.
right.
So we're just going to end up with, and let me think for a second. I think so. Sorry. What I'm suspicious of in this code is that J is going to run all the way to the end. But that is in conflict with this loop invariant we like, just in the sense that we don't want these 2 sequences to overlap. That we're having I and J define these sequences, and intuitively we want them to be separate. Because they are a separation of 2 halves of those. A theoretic. So I'm trying to think of where exactly we should place the break statement.
You should place the break.
Yeah. This is probably a slightly different partition than one. There's a few ways of implementing partition.
I did mine after as well. But I think you can.
So like here? Oh, okay.
Yeah, actually, you had house pass. I had house break. But I'm not using a for loop. I'm using 2 while loops in this statement.
Okay, like while true, wrong.
Yeah, basically just while I is less than J,
Yeah.
and then while array at index J is greater than it was also while.
Oh, so that's
But no,
it's here. If J is equal to I. Okay. So this is sideways. So this is saying, so you can imagine, we go one more iteration. And then J is here, and that's still good. We do the do nothing case. And then J is incremented to be here. So now J and I are equal. All right, we're done. And we exit the loop. And then yes, J and I are both pointing to our sort of our midpoint. So we can turn. So modular models, yes. So I think that this should feel a little confusing because it feels like, well, where's the sorting? That sort of was always my question.
The sorting is happening in the function where you add, like, to the output of the two quicksort methods, like the recursive calls, right?
Isn't it happening with the swap?
Yeah, so in a purely mechanical level, this is the only place where we're moving elements around in the array. So kind of like that is that can sort of be our starting point. It's like, all right, here we're actually moving things around. So here's kind of where we must be putting things more sort of order. And there's that intuition of like, okay, we're kind of getting it more sorted, but we're not, we're not getting all the way, but at least we're dividing things correctly across the disk. And so what we can do is we can see this in action on our favorite input, 5, 2, 1, 3, 4. So I'm not going to go on that way. But we can start quick sort, QS. Where it's this array, and then 0 to 5. And then we call partition. And it's always going to be this way, because we're modifying it in place. So I'm just going to have the sequence 0 to 5. And so what would that do? We choose our pivot, is this element. And we also start our I sequence at that point. And we start our J sequence at this point. And we do what we did before, but we go through and say, okay, J is going to increase by 1. And then say, well, is this 5 smaller than the pivot? No. So we do our thing where we move I here, and then we do this 3, 5. And then we happily move J to here. And then is it smaller than the pivot? Yes. Is J smaller than the pivot again? Yes. Oh, and now they're equal. Literally, they're integer 3. So we have m equals 3. And so now we're done with this line. Like we call our quick sort array 0, 5, we call partition, we're done. Then we call quick sort the same array, like literally the same array. So we already changed it somewhat. So now we're recursing, which is a little annoying. And we have partition. Yes. 0, this 0, and then this 3. So where do I put my I's and J's? So I is
I will be 2.
and J will start at. And then we do the same thing. Is this bigger than our pivot?
Yes.
Yes.
Okay, so what do we do?
That depends I.
Yeah, so we do the.
I is now equal to I minus 1, which is 2, right?
Yes, oh, I might have lost that one there. Oh, no, sorry. 3, 2. So this is, I is now pointing here, and then we have successfully advanced J to here. and now they're both equal. That didn't do anything, which is a little concerning. There's my, sorry.
So we said that the middle point will be 3. That will be,
Sorry.
no, I'm not.
Okay, bro. I left that, which is swap. So this is that thing. Oh, okay, it didn't work last time. We'll do it now. Swap of A E sub -1, and then I. And that's the main thing. So I'm going to write it down. Pivot is in final location. That is a detail that I should have given down. So we're patching things. We got that for free in this one. But here what we're saying is after we get this, after we've partitioned our array, we want to make, oh, we didn't get it for free, yes. Why did I do this there? We want to make sure that our pivot is in its final location. And we can do that because this sequence is everything greater than or equal to it. So if we just place it at the beginning of that sequence, then it's in its sorted location. That might feel a little magical. But to be explicit, so this is how we ended this partitioning step, right before this loop. This is how we finish this loop right before we exit. There's this final swap. And then that just means we, in this case, we swap these two. So we end up with 3, 2, 1, 4, 5. And right, like this, we can kind of see that's where it belongs. But again, we're exploiting that idea. Because this sequence is everything greater than or equal to the pivot. If we place the pivot at the beginning of that sequence, so we do that swap, A, so on, then that just means, great, this pivot is exactly where it belongs. We don't need to sort it anymore. So, that in mind, if we added on that last step here, we'd end up with 1 and 3, which is what we were supposed to. I'm glad the air conditioning was there. So we partitioned 0. So that was an interlude. Now we finished partitioning from indices 0 to less than 3. 0, 1, 2, or 0, 1, 2. And so that was, remember we started with 0 to 5, then we finished partitioning, then we called this recursive call, we partitioned there, and we'll end up where so here, rather, what was the final I we ended up with? We swapped, yes, well, everything is greater than or equal to it. So I is 0, so n is 0. I sort of jumped ahead a bit. Do you see what I did there? Where, when we were looking at this subsequence, we're always building the ji, and we return I, and I is going backwards. And it's like, it's the sequence of everything greater than or equal to our pivot. And here our pivot was 1. So I'm going, okay, well, what's the index of our pivot? The index is 0. So n is 0. And so in our recursive call, first we call quicksort with 0, 5, and then we call quicksort of 0, 3. We call partition 0, 3, .n equals 0. And now, whoops, we need base cases. If E minus B is 0. So building that up 5. But now we can call it recursive quick sort 0, 0, right? So what? That's sort of the empty subsequence, right? Is that sorted?
Yes.
Okay. So we return, right? And then we sort from, and this is again where I'm doing these little tricks. Yes, I think this should be +1. That doesn't seem. I told you there's going to be off by 1 error somewhere in this code. Yeah, so in any case, we have quick sort of 0, 0, that was easy. And then we have quick sort of 0 to, yep, that's, yes, this is the sort of the m plus 1. Why is that? Because we know m, the value at index m is in the sorted position. Because of this trick that I initially left out. And so here we're saying, we know we're cheating a little bit. We're saying we know this guy's in the first position because he was our pivot before. So what's left is we only know that these are bigger than our pivot, but we don't know if they're sorted yet. So we call quick sort. And then we can go down the recursion back up and so. Do we believe recursion or do we believe quicksort now?
Would it work for if you have like repeats? Is that?
Yes, that's a fun question. As in general or in this implementation?
Well, yeah. Well, I mean, imagine in general.
So, like any sorting algorithm should work with repeats.
Yeah.
Like all the traditional ones, certainly. An interesting question that comes from that is something called stability of sorting, which sounds familiar to someone
Yeah,
who would want to explain to everyone else.
I can't put it in the right words. And I don't have a notebook where I wrote down a good explanation.
So I'm going to erase quicksort because I think we're wrapping it up. And then I will talk about stability, which comes up with repeats. So I'm going to erase it.
Yeah, sure.
I guess now that everything's recorded.
But every sorting algorithm has stability, right?
Not necessarily. So let me. And like stability is a pretty general word. So.
Yeah, I was gonna say, I think it explained that.
Yeah. So here is sort of a weird list. And there's two things. So obviously there's the numbers and then there's also colors. Because I only have red and black markers, so red and black numbers. So like this is to capture the idea that you might have an array, not just of numbers, but of like structures. So this is a number and a color, where it's a person and a birthday and a hometown. You know, it's that you have to choose one thing to sort on, just one dimension. And so if we sort this, we might end up with 4, or we will end up with 4, 5, 6, right. 4, 5, 6. Don't worry about problems, you know. 4, 5, 6, 8, 3, 4. So is this the sorted version of this array? Yes. Yes, it should.
I'm sorry. Can you explain the red thing again?
I'm just saying that we're sorting elements, and these aren't just numbers; they're actually like structures or objects or classes or whatever, that aren't just a number but also a color. This is just a very quick short call that you construct for class or other int number, and you know, color C. Where C is red and black.
I see.
And what we're doing is, you know, sort by number, you know, or array. So we could either, and what I want to introduce is the idea that this is sorted, as is this. So this array is, or this is this array sorted, as we just, I got you all to do that. And this is this array sorted, right? Or, are these two arrays equal?
No.
No,
All right, a few people are saying no, why not?
because for the second element in both arrays, they're not equal to each other.
Yeah, something weird is going on here.
Would you say the reference is not the same?
Oh, yeah, I would just say they're different values.
Yeah.
They're equal on the thing we sorted on, they're all 4. But in the other things that they're different. So in this case, it's literally the marker color. But you can imagine the quintessential ones like people, right? So there might be 4 people named John Smith, but if you sort by name, it's like great, and they all have different phone numbers. And that is the idea. So that's motivating idea of stability. Where if sort says it's stable, it says I promise not. It still never even looks at this, but it says I'm still just going to sort them according to the number, but I want to equal ones. I want to keep in the same relative order. So because this 4 was before this one. This is the stable sort, or this is the result of the stable sort, and this is the result of an unstable sort. So, I don't know how to sort of give an example, illustrate this, but it's not that it's looking at the colors and saying, oh, when everything else, we should put the black colors before the red colors. But we're just saying this one happened to be before this one, so when we finish sorting it, it'll stay before this one, or this will stay before this one. So in fact, if I want to be really thorough, I've done something like have a red 5 here, and then in that case, to maintain being a stable sort, that red 5 better precede the black 5. And just drag it home.
So the stable sort just keeps things in the order that they should be, or originally presented.
Yeah. And why might we ever care about this?
Because you want your sort to be predictable and just make sure that given the same input, it gives you the same output.
That's true. That's definitely a good thing, especially if you want to test it. Want to help narrow down bugs. It also helps, and sometimes this helps me. I suppose you're all using Macs because they're cool. I'm looking around and I see lots of Macs. There's a computer in the back. Nope. All right, it's also Macs. All right. So I see. Okay. I'm sorry. I thought there was a much.
Oh, okay.
So like a game. But so I don't know about Mac, but I know the Windows Finder you can sort by name and then by date and so on, and you can click it source that. Right. I'm sure there's something similar. But what you can do is you can sort by name and then by date, and it'll be a stable sort. So you can say, oh, I know it was, if I have the game with B, they say, great, now I have all the B's, and I remembered it was sometime last week. So you can keep all the B's there and then sort by B. That's sort of a very human example. But more generally, it's like, if you want to first sort by, if you want, stuck with the colors, I guess, but if you want the red elements to be before the black elements, you can just first sort by color and then by number, and you sort of get that hierarchy here.
Yeah. So when I back up the MacBook, right? I do 2 backups in the same day. It's going to show me the earlier time and then the later time. Like that.
I guess I don't know how the backups really work, so I'm hesitant to, or like this is in the file, as in I don't know what image I'm supposed to be seeing. But yeah, probably, if you want to sort by file name and then by date, is that what you're?
No, just because you mentioned the MacBooks and sorting, but what I'm thinking about is the memory. Like if I back up something or something is done on the same date and I look into it, something's done on the same date, it's going to have the same date, but then it's going to show me backup was made at 1,500 hours and then another one at 2,100
Oh, yeah.
and then that way, it'll put it in that order instead of having 2,100 hours of work, 1,500.
Yeah, I mean, it could be maintaining that. Yeah, so it comes up in real life. Interesting. So, to be honest, like I've never in in industry in the job or whatever said like, oh man, I need a stable sort rather than an unstable sort. But like I've heard from it, like in my day-to-day, I use it sort of as a user, and like I'm sure it'll come up. And it's sort of like the sorting 102. Like if this stuff is sort of you got to have these algorithms, like oh, what's stable sort? That's sort of the next piece of the tree.
I had an interview question that kind of involved that. It's like, if you give a string, sort it alphabetically, but basically, if there's like, let's say I and then uppercase I, maintain the order. So make sure if the uppercase I appears before the lowercase I, just maintain that order. Even though they would be the same, you would have to sort them, relative to each other, I guess.
Yeah, so that sounds like, you could either try to say, okay, well, let's sort everything and then do that whole subsequence trick. Like,
Yeah.
let's sort that using a different comparator. In other words, comparator. Things you do say as a comparator.
If you compare ASCII values,
For that one, yeah, so that's what Swift does by itself when you sort like letters or characters. But yeah, I had to like work around that.
so you guys just don't do anything, so you just like,
You walk right into that.
wow.
But no, I mean, like, so in real life, of course, with strings, especially, like, there's the knowing how, like, understanding how the tools that you use work, and then it's also people will try to provide useful tools. So there's that frustrating thing. You should never, not never, but think really hard before implementing your own. No matter how much you love quicksort or merge them, think really hard before implementing yourself. Just as chances are, someone else has implemented it and just tested it off, and then
Do you think it's easy to get implementing these algorithms to get an unstable sort, like by accident?
So quicksort is basically always unstable.
Always unstable.
I'm just saying, like, because when you're doing the partitioning, or my intuitive argument, or my field theory, that when you're doing the partitioning, it's not clear that you'll maintain the right order. Quicksort's unstable. Oh, and sorry, I should have also talked about this with quicksort. That we chose the partition by somewhat arbitrarily choosing the element. Perhaps there's a bit of, dusty memories where you heard, oh, sometimes quicksort can be O of n squared.
In the worst case.
Yeah, worst case.
And how is it that that comes up? And for the sake of time, I'm going to imagine basically that when we partition, so we always have m equals partitioning portion, or when we have quicksort of 0 to n. So n is some partition.
Is it when the pivot is like the largest or is the smallest possible value?
Yeah. And so partition is always going to, we forgot about performance stuff. You guys are always doing. This is going to be O of n, or O of n time. Right? Partition, we always go through the whole array. And if m, equals n minus 1, they'll set up that trend where basically very slowly go through the whole array. So one of the ways people avoid that is you choose the partition element at
Random?
Yeah, you just, instead of saying that's going to be, you obviously need a different implementation. So you basically say, oh, instead of choosing always the last element of my subsequence, I'm going to choose a random element in the subsequence. Another funny way of sort of implementing that is just randomizing the list before you sort it. But whichever way you do that, that is going to lead to an unstable sort. I hesitate to say like, oh, quicksort is intrinsically unstable, like Schroeder's people have been very horrific with this sort of, like the usual way of talking about it. Yeah. And I guess I sort of skewed this. So we have, in terms of y, so how long does quicksort run? Yeah, what's its runtime complexity? Just as like a general question.
In log n.
Okay, so usually n log n, more formally the expected value of its runtime can be expressed as n log n. There you go. Why is that? Usually, so I was saying partition, I'm sorry I erased some of the code, but partition takes O of n time because we're basically building I and j towards each other and they have, even if they're both incrementing by 1 each time, and that's still half, right? So it's a little bit, that's O of n. And so you can imagine that, here's our root, and let's say our pivot is always exactly n over 2. Obviously, there's nothing around here. Then you can say, all right, call quicksort twice, one on an array of size n over 2. So we kind of think ahead. When we get there, we would partition that half size array. And then we have, those two halves.
And then you just keep going.
Yeah, and you have n over 4, and obviously, we will get to a point where n is 10. And we divide it by 16 or something and start getting zeros. But okay, here's our favorite data structure tree. And so you can imagine this sometimes how we go. So this is not rigorous math, but this is a tree, right? We love the trees very well right now. What is the depth of this tree as a function of n? So n is 8. How deep would this tree be? And what I mean by that is, so here is when it's 8, here n is 4, here it's 2, here, n over 8. This is 1, and I guess I'm intuitively suggesting the intuition that like at this point, because we say, all right, it's going to be 1, we can't divide that in half anymore.
What was the question? I'm sorry.
How deep does this is a tree. It's not a data structure, like we're not building this in code, but this express the idea of how long this quicksort takes. Oh. So I'm saying basically this is like how many recursive calls deep will we go if n is 8? Oh, okay, first we have to partition 8 elements, and then if we're perfect and we always get a midpoint partition, we start at partition 4, and then 2, and then 1, and then kind of just, we have that big space. No elements return. So say, okay, we don't call partition anymore. So it's depth 1, 2, 3, 4. And what happens if n were 16, which is twice as much? Close. We have not found error, as always. Or which is to say, that's always the error in computer science. Before we had 8, 4, 2, 1, I have 16, 8, 4, 2. Okay, we need 1. That was a little trick. So, okay, what happens if n is 32? How deep is the tree?
It's more than the deep.
Yes. So 8, the depth is 4. Whoa, that's not 8, that's 8. Depth 4. 16, the depth is 5. 32, the depth should be 6. Okay, so we see the pattern. I'm doubling the number of elements, and obviously, if there's 20 elements, presumably some of these will be 5. But roughly, this just has a pattern log base 2. Okay, good. At least one person knows this. Is this super familiar?
Like high school, right?
No, in high school, you usually learn either log base E, that's one of those, or log 10. But the intuition for log base 2 is how many digits it needs in binary. Plus 1, right? Like I was saying, I always did off by 1. But so for instance, 16 is, oh, okay. Yeah, you need 5 bytes to express the value, 5 bits to express the value of 16. Because it's, 1, 2, 4, 8, 6. So this is 16 in binary. This is 32 in binary. So 10. Yeah, just as in, that's just one thing. Don't get too excited about it. But the point is, okay, so this log n is going to relate very closely to this log n. That's just, I'm starting to panic you, I hope. And here's a silly thing where, here's a fun observation where this is our root of the recursion, right? We call partition all the elements. And then intuitively, we're having this call and this call. So we're partitioned. So here we're doing O of n work in this first recursive level of recursion. How much total work are we doing in this level?
Same.
Twice, right?
Yeah, so it's n over 2 twice.
Yeah.
So the end result is the same amount of work. And this is sort of like a silly thing of like, well, before we sort the whole thing and then we look at each half and we partition those, and of course it's like, there's always a lot like 1 error, so we're speaking for all these. And then each of those, of course, are partitioned. Now we have 4 things of n over 4. So that's also an error. And again, this is not a rigorous math proof or all that crap. But we have n plus n plus n plus n. How many times? Log n times. That is n. I know I'm just sort of like putting things like next to each other and saying cool, like it works. But like that is kind of the outline of how you really convince someone, which is all proofs, that the runtime of quicksort, if you're always able to make this division nice and neat, or you always get n over 200, that's expected runtime.
And like there, it doesn't have to be n over 2, it could be n over 1. And then the other side n over 3, just to make sure.
Well, so it's exactly when these start going not over 200. Yeah, so if this were n over 1, or well, okay, this would be n over n, or something. It gets a little weird. But the issue is that every layer is always going to be, and this is looking at what the cursor calls a little sideways. Like all of these layers are always going to be O of n work. So it really depends on how deep you go. And the more evenly you can distribute the work, the shallower the field. And so it's exactly that's why when the array is already sorted and you're not really partitioning anything more, you basically end up with n minus 1, n minus 2. You get a very, very deep tree. Every layer doing over. That's how it becomes expensive. But there's a lot, this guy's just sorting stuff. It's very neat. And so will this ever come up in your life? There is some intuition of like, oh, if you split work with the expectation that it's sort of split evenly, like make sure it's really split evenly. A good rule of thumb, I guess. So I think we've done a quick sort to death. Move on to merge sort. If there's any other. Oh, okay. So yeah, we covered the working implementation of quick sort. Stability, the question of stability in sorting. Some kind of hand-wavy analysis of the runtime of quicksort. One thing I'll point out is that we don't allocate any new memory for quicksort, right? You're always just modifying your own place. So yes, you got the space for this call stack, but in a good world that wouldn't add up to much. The merge sort is going to look suspiciously similar, but it's still different. So do we feel about merge sort about the same as we felt about quicksort?
I feel better about merge sort. Because like other than today, I've really used or attempted to do quick sort, but in a lot of like different interviews or just studying, I've used like merge sort more.
So we've had like questions that say, please implement merge sort. Interesting. Did you find those reasonable out of curiosity?
It was
Like, as in, was it just like implement merge sort, or was it like hidden for?
first it was basically like how does merge sort work, and then I explained how it was like divide and conquer, and then it was like, oh, okay, would you be able to implement it quickly? It's like, yeah, okay.
So I won't put you on the spot anymore. I mean, you're welcome to it.
I could explain it. I could explain it.
Well, how about I ask someone else to describe how merge sort works? Make a code review that. Or not.
Merge sort? So in this case, it would be similar to what we were talking about before, where we sort of make two arrays. Like we split it.
Yeah.
The direction is a little different.
Yeah, like we split it and then combine it in some, like merge it in some way. After shuffling stuff around.
There was another question, or is you guys good? All right. Well, then I'll start the discussion with an actual reference. I don't know how to make a font like that. So, merge, sort, we have array A. We're actually going to think about the base case. Length of A is less than 2. When would that be?
And one empty array or one single element array?
Yes. Both of these are sorted.
Yes.
That's why I know that. Turn A. Otherwise, M is the length of A over 2. Full stop. And that's not to say we're done, but as in like, and we're 4 as well, it's a result of partition. Here we're just saying, no, let's just cut in half. Then we have X equals merge sort. And here, this is neat syntax to know. Not all languages have it. That's what we're talking about. Why? A, M. Merge. All right. So again, with that annoying, like we haven't implemented it all yet. This is merge sort. That's it. So what's that? First, this is interesting syntax. It's used in Python, but it's used in other programming languages, not just math. And the idea, whatever the syntax is, the idea is pretty neat. So this is an array slice. People talk about slice.
Yeah.
We have that.
Oh, this is in Swift?
Yes.
Yes. Okay.
It's not the same, but we have the slides.
Yeah. Like, wait, sorry, with the syntax or without the syntax?
The nice syntax, but we have like arrays.
Okay. So if I have an array 1, 2, 3, so this is A, then I do A, 1. What this is saying, let's see if we all have the same slide. This is saying implicitly, all right, from the beginning, because there's nothing on the left hand of this. Another syntax would be from 0 to 1. Up until but not including 1. You'll talk about that. So that would be this. And then you can have like A, 1, 2. Okay, let's make a little interesting. 1, 3. Which is 1 up until but not including the index 3, so that's these two.
Does this create a new array and copy as
That's a good question.
slice?
It depends on the language, I'll say, in an annoying as in Python, it does create top. And we'll get to that, or the implications of that in a second.
So it's like close range on the third one. So it's, 1 and then less than 3. It's not like from 1.
Yeah. Yeah, so it's index 1 and index 2.
Okay.
Or it's index this up until but not including index that.
Okay.
Which is a little.
What's the name? I think I have heard of the name of this syntax.
I just know that's slice array slice syntax. So here the shorthand is the colon is 0 to suggest the idea of slicing sort of line. And the shorthand is that. So just zooming in, this is sort of the same as A and the length of that. It's just a shorthand. And in a similar way, M is just a shorthand of A, 0.
So why not just use ranges, like a closed range and open range?
This is faster than typing.
Oh, okay.
And then, like, alright, that's a little tricky, but like, it's just,
More intuitive.
sorry?
I feel like it's more intuitive.
Yeah, I guess it's, or, sorry, I'm thinking of Python ranges. What do you think of? If you're thinking of Swift ranges, that's kind of very familiar.
Yeah.
So I guess that's not fair, I don't know what they are. But like, by that you might say like, oh, the range of,
Like you could make an array with a range, that's what I'm
Yes.
saying. Yeah.
So there are, I'm guessing that there's similar, like, there's only so many constructions in programming. This will give you a list that you can index into, for instance. So I don't know if you can do that in a range. You can do it like a piece of J or whatever.
Yeah, we could.
Not in a range. In a range? I don't know.
We could subscribe an array.
Oh, you
No, but can you subscribe the range?
I believe so.
I don't think
You don't think so?
They're different. Some,
Is the range just from one index to another?
Yeah.
So when we just make the index array dot length, the array dot length.
think we're getting a little.
In any case, yeah, I think we get it.
Well, and then, well, just to clarify one thing, this is really passing the, like, a subsequence of the array, so it's not the index or anything. If A were, 100, 500, then 2, or A sub 1, A lost 1 is going to be the sequence 100, 500. It's not the indices, it's the values in the array. Okay, just making sure. But anyways, we now know what we're doing with our parameters. So, up to your language, you know what this line is doing already. We know what this is doing. We know what this is doing. This or recursive. We know what this is doing. So this is the only thing left. So what is merging? Write it up here. Maybe a little narrow. So we have x and y. So I think I probably renamed the parameters here. So has anyone encountered, I guess one person's implemented merge sort recently. But do we have a sense of what merging might be? And would someone like to try to explain the idea?
I think we want to merge the values of x and y in a sorted order. Which might be, I think we could accomplish by looking at the first value of x and y, of x first, comparing to the first value of y, deciding who should go to maybe an output array.
I like the idea of the output array. So yes, you're thinking of the implementation. Yeah, details. Here's our output. But yeah, actually, let me take a brief interlude. Okay, great. And so before I was introducing the idea of partitioning in quicksort, there was an idea of like, oh, this array is like more sorted than that one. So you can imagine appealing to that same sort of idea of like kind of approximately get sorted. Here we have, 5, 3, 2, 1, 4, 6. And let's say we split it in half. 6. So if we take this array, it's not very sorted, right? And we split it in half. And here we're not partitioning it, but we're just going to sort each hash separately. Like separately, I just mean pretending as if we're only seeing this happy array, let's sort this happy array, let's sort this. Just intuitively, that feels more sorted. We're getting there. And that's what's going on here. So we're saying, let's cut this array in half, and with magic or with crude, we're saying we don't know how to sort the array of our final length yet, but we know how to sort smaller ones. So we'll sort this smaller one, this smaller one. And that's the hope that it makes things easier. And so merge, as we will implement it, the idea is that it will take two arrays that we promise are sorted. Right, like as in X is the result of the merge sort call. The merge sort is supposed to sort something. So X is sorted, Y is sorted. And now what we want to do is we want to somehow merge these into 1, 2, 3, 1. Right? Suspicious? Anything suspicious about this? You guys just trying to get this? I just want to see it implemented. So much excitement. Okay. It's late when this stuff isn't exactly what you want to keep. Like I don't either, to be fair, but it's fun. It's like solving a neat problem that once you solve it, you never have to solve again because you have it in code. It's the big appeal of this stuff. Yeah, it's like making something. Anyways, we have an index I, we have an index J. These indices are much easier to reason about, in my opinion, than for partitions. This is just how many elements from A we have merged. So, right, C is going to be the result of our merge. Very end, we're going to check it. As Alejandro was saying, we're going to have an active variable, we will return C. And I is how many elements of A we have put into C so far. And J is also how many elements of B we've put into C so far. How might we do that? Well, when do we know that we still have some elements to insert?
The length of A.
I'm glad that many people are talking about it. Actually, right? Yeah, as the new person, what do you?
When the column is greater than 2.
I'm sorry?
The column
Hmm?
is greater than 2. You said, how do we know when we have?
Oh, yes, okay. I'm thinking length. So like the counter length of A when it's bigger than I.
Yeah.
Okay. And also similar for B and J. I ask pointedly for whoever. Yeah, but that's sort of exactly like, okay, we want to know, we want to do something so that I increases to be the size of A. And same with J. So, a little bit in interest, in the interest-ish of time, we can say while I is less than the length of A, and J is less than the length of B, and so I took the wheels a little bit, right, I guess. But this is saying, okay, while both of these still have something that we would probably want to merge in, what should we do? Now here I'm going to just let go of the wheels a little bit.
We should check if A sub I is greater than or less than B sub J.
Okay.
B sub J. And then if that is the case, then copy A sub I into C.
So, okay.
Let's do the reverse.
So I like this. What in sort of, so be subjective, intuitively, what does this if and else column mean? Like what are we trying to express?
Copy them in order. I guess like I'll say this, like where the actual sorting is kind of happening.
Yes, that's fair. Yeah, well, I would say that, we're always wanting to plug it, oh, sorry.
Yeah, you're basically comparing each element to the same, well, yeah, so, we start off at the same position.
There's a few models here.
Yeah, you start off at the same position, and you just compare the elements at that position, and, if it's less than, then yeah, you append it.
Yeah, so I would describe this as saying, we're always appending the next smallest element we see.
Yes.
Something like that. I'm not saying that's the right thing to say, that's sort of how I think I'm getting wrong in there. In terms of making things a little bit more reactive. So intuitively is that we're taking, you can imagine almost we're taking it out of B and now placing it into C, and so we kind of want to implement J to capture that idea. We're ignoring everything from E before J, like we've already processed that. Need more room. And let me just make sure I didn't do something different. And so here's just some nice sanity checks. Think about where we can, we will this loop over and.
I have a question. Does
Oh,
it include the middle element? Like, that one is inclusive, right? That we talked about before.
Oh, fair enough.
Like X.
So yeah, I like the idea of synthesizing this with quick sort. But here there really is the notion of middle elements because.
No, I meant in X and Y. What they're including the middle element in Y, I believe.
Yeah.
Okay. I was confused about that.
Oh, it is.
Yeah.
Yes, this is, if you're familiar with, you know.
Yeah. Open and closed.
Yeah.
I see.
It's like that's another one fun thing about the slices and yeah, so here, and this is a nice sanity check. Whenever you're writing a loop, especially in the interview question, will the loop terminate? Or will the loop end? But before we have this, you can ask, will this loop end?
No.
Is there, whoops, gotta have at least one of these grow, we hope. And you obviously that's just a bug. But that's also why if your language has something like Python, for I in range of n or whatever, it take care of that for you. I is going to be for any performance in general. Ain't that be easy, unless if you change. So this is not quite done. I could have an adversarial. However, all right. For instance, let's say A were 1, 2, and B were 3, or 3, 4. What a wonderful and easy situation. So what we do is we have I is here, J is here. Oh, sorry.
Is in the first one compared with the first one and then.
And so C would then be. So we'd say, okay, A sub 0 is 1, B sub 0 is 3. So that's this case, so we append 1. So far, so that's where we hope.
Yeah.
Then we increment I.
Mm-hmm.
And then this is the else, so we'll do it all the way back. So now we have A sub 1,
Yeah.
which is 2, and B sub 0, which is 3. So it's this one again, right?
Yes.
So we do 2. Then, and then I, what value is I? So I is not from first was 0, then after we add this was 1, and after we add it again it's 2. So now this is false.
Oh, so that a little bit.
Yes. Okay. And that's just the idea.
Oh no.
Calculating it. So this is the
Right.
as we've written. And that's just to capture the idea, like, well, if we do a sub 2, we're gonna hash. So let's not do that. So we're not, and clearly C is not what we want it to be. Just because it's not done. So what can we do after the loop? Or what can we do in general? I think we should do something after. Oh, the intuition in this case is that when we're done with this loop, it's sort of like the opposite of the loop variant. At least one of these is done.
Yeah.
Just because it ended, so one of them.
Yeah.
So, and what do we want to do with the remaining one?
I have the answer to this, so that's what I'm saying.
Oh, okay. You were saying that while you had your I have the answer.
So I'm just saying, like, I already have the answer, so I'm like,
You combine them, or?
So there's this extra little jump, I guess, I don't know how to bridge it except just to sort of say, which is that, all right, so each of the lists individually are sorted. And we've been going through kind of peeling off the smaller ones each time. And if anything has elements left over, those aren't sorted over just lists. And they're bigger than anything else we've ever seen.
Oh, okay, so we are, oh, so we just add, yeah.
Yeah, we just-
combine it, yeah.
But we're good.
Okay,
All right, now you were going to say that, I'm gonna cut you off. Okay, okay, sorry.
sorry.
I don't need
All right, so let me just get it right. Let me just do this the right way. Yes. If I is less than the length of A, C, this I got some next. So C we can append. So here, appending is adding on a single element to a list, and then the plus equals is concatenating the lists together. And here's that wonderful slice. That's, oh, oops, that left. Okay, the length of B. C plus equals B, so okay. Yeah, and this is just, if you're implementing this for fun, which I know it sounds silly, but really writing out the code, even seeing it written out here, okay, helpful in solidifying things. So I would recommend it, this J, D, A, oh my gosh, you're gonna make a typo anymore. That's fine. So you do it now. Anyways, and that's it. My first one. And I actually tested this once, this one works. Are there any, so if we feed the merge sort, are there any suspicions or any questions left? So here's the leading question. For quick sort, we were modifying the array in place. What about here?
We're making X and Y as, sort of, yeah, they're like copies, because C is a new, instance.
Yes. Okay. And so that is a real cost, I guess, for merge sorting, over group sorting. And allocating memory, if you're sorting 100 things these days, it's not a big deal. It's not like you're allocating memory that is something better than it's a huge thing. We're in trouble. That's true. I think there might be some super clever way of avoiding that, but I don't know. It's sort of hard because it's I don't really know how that works in the first case. But, is this a stable sort? how would we even figure out if this is a stable sort?
I want to say it is a stable sort, only because from, you said before, and from what I understand you were showed to be, it breaks down, it splits everything in half. So because it's able to split down everything in half down to, say, one-on-one comparison, then it's more likely to be stable.
Okay, so I can be sort of the gadfly and say, well, hold on, we're breaking things in half, a quick sort too.
Yeah, but you're just cutting the array once, right? No.
What was the source of instability on quicksort?
So in general, with quicks, I guess the intuition behind saying quicksort isn't stable is that in general, we would pick sort of a partition element, kind of arbitrarily, and then we kind of scatter things based on that partition. So I think maybe, Daniel, what you're getting is that, well, here we're sort of more gently cutting it in half. We're just sort of saying, this is that we're not throwing things back and forth.
Exactly. We're making sure that they're sorted before we even merge them. So in my head, if we're doing that, so almost the word I'm going to use it down to that point, then we should have less room for less room for less stability.
Yeah. Instability doesn't seem to be able to sneak in.
Exactly.
Yeah, so I mean, I like that intuition. What to kind of hone in on it, we can say, well, so yeah, what sort of we're not really even swapping anything, but we're sort of plucking things out of X and Y or A and B and putting it in. So kind of, it's weird kind of working inside out. So let's start all the way in here. A is already sorted, and B is already sorted. So there's like, let's just assume that there's no instant, like those have been sorted nicely. And then if we have a sequence of equal elements, you know, 4 that's green and 4 that's blue and 4 that's red and so on. Well, then they should all, like, they might be kind of split between these two. But even so, yeah, I guess because we're doing A first. Yeah, even so, we're still kind of talking them out in the order that they appear. So okay, it seems that we're maintaining stability there. And then, you know, it's all very hand-wavy, I'm not trying to prove anything. But it's like, okay, so this, if we're given things that were stably sorted, then we don't seem to introduce any instability. And then, well, what are we doing here except just merging and merge sort? And if this is the only chance and we don't introduce instability here, okay. It's not proof. If someone really wants to drill into it, they won't believe that. But that's sort of the starting point. That's how I would start really trying to argue about this. Again, in the day-to-day, what we do is with the API documentation, use control F state. It should say explicitly if it is or isn't. Or what
Do you know of any research where I could read about how they discovered these like algorithms?
Wikipedia. I'm trying to merge. I mean, these are all probably around the 60s. I'm sort of making that up, but that's when most of these kind of came up. Sorry?
Instead of computer to the home.
Yeah. Basically, online, you know, so they really care about speed of even sorting 100 elements.
I've tried to, is anyone familiar with the website Visual Go? Visual Go. Visual Go. Like, it's like visual and algorithm in one word. And so they have the sorting algorithms and they there's an animation.
Oh,
Oh, it's like the song? Is it like the?
Oh, this, okay, yeah, okay, yeah, I think I know.
But then like they don't describe the algorithm, they describe like pseudocode
Yeah,
for it. And I try to like just look at pseudocode, see if I can come up with a code, but I have not
I see.
succeeded.
their explanation of
Oh,
linked list is really good.
Okay, great.
Yeah.
Visual.
Move.
Is it this list?
You want to project that, go for it.
Yep.
I can't help you. Um, And this is, in terms of translating pseudocode to real code, I have always, so that, and we see it, it's like, they just see this. Oh, I see, shit. Oh my god. That's what good. Yeah,
Someone said recursion.
Yeah, pick any one.
quick typing in that. So don't worry, I would recommend not wasting your time on this.
Okay.
Maybe that's a little bit, but like, insertion is much a sort, I think, of like much more clear. Bubble sort is very easy to analyze for its runtime complexity, but like, it's not a very intuitive analysis.
So let's look at merge sort, which was what we're doing.
Yeah.
So that's pretty fast.
Oh, I see. Oh, I see. There's a little speed thing.
Yeah, and then on the right, it gives you like the scale.
Like this pseudocode split each element into partition of size 1. Recursively merge adjacent partitions for one equal left part index to right part index. If left part index, left part can't be referred to right part can't travel. Copy left part to the back. That's what we're doing here. Now let's copy right part. Copy them to it.
So this is a nice piece of. Yeah, you have whatever works for everyone, of course.
Here we go.
There's also YouTube videos that does stuff similar to this, but does it in like song, and so it's like kind of
Some Hungarian folk dance or something.
no, it's like a little like tingle every time it like sources.
Oh, if it's like a less than comparison.
Yeah.
Yeah.
It's kind of addicting though. To watch. It's kind of
Yes, okay. Yeah, I mean,
kind of hypnotizing.
yeah, say that, you know, really, like, you know, deeply understood.
No, I was saying it's for fun. Yeah.
Okay, so we have 10 minutes, I think is more or less what I want to go over. Either on or off camera, I'm happy to hear feedback, like this versus the more traditional questions. You know, what's piggy and stuff. And yes, we all like the explicit code, right? I found too stupid.
No, that's good.
Wait a minute, was that right? Is it,
This one has,
no, I mean, is it, what's the word?
oh, stable?
Stable?
Yes.
It is. For that reason that we're going down.
Yeah, like a true skeptic would still be, you know, saying, oh, what about this thing? Like, yeah, that would be the seed of the full argument.
Could we decompose the time complexity?
Ah, sure. So this is, well, end up basically drawing the same. But so here we have, you know, here's our root recursive call, or not recursive call. We have some array length n. This is constant time. This is constant time. And then we have two smaller calls, you know, and which will take however long they take. And then we have a merge. And so this is, x is always going to be the size n/2, and y is always going to be the size n/2. And in general, how long would this loop take?
The length of each pair.
Yeah. So I mean, more or less, and like,
And
yeah, that also, and even if we jump straight to here, basically is we're going to be doing the copy anyways. So the end result is we're going to copy every element from A and every element from B into C. So this merge is going to take O and B. And so, all right, that's this. And I go stuff, clean up these recursive calls, what they mean. Well, M is always going to be N over 2. And so just sort of jumping ahead a little bit, this is N over 2, and O is N over 2. And then same, and I wrote N over 2 here for the same reason that we end up with an array of half the size of the previous array, do merge for it, which is still going to be O of N. And so the tree I'm drawing here is the exact same one as I do for quicksort. If anything, I was sort of being a little bit more deceptive with the quicksort tree, because that was saying, you know, we're hoping that when we partition things evenly. That was a quicksort. And by saying, okay, if we partition things evenly, we always have N over 2 and N over 2. Here, we always get N over 2. We're always splitting it nice and evenly. We're always going to have, you know, a tree of depth, you know, log base 2 of N. And so we're always going to get N log N runtime. And I say N because this will always sum up to N, this will always sum.
Is that log 2 of N the same thing as saying N log N without a base?
Oh, it's base 2.
Yeah, I don't know, like, this is what I've seen this, other people use this, I don't know if it's like super powerful. In terms of, I won't get into this. You can, in big O notation, or log. Oh, this is from memory. I hope it's correct. I think it's correct. As in big O notation, you can ignore what the base of the log is. They differ by a constant.
I think I read that in second opinion.
Yeah, some of those levels, it's like log base 10 over log base 2 times N. That's good.
And you were saying that so this merge sort is slightly less efficient on space.
Yes. So, yeah, like roughly speaking, you're always going to need to have a second array.
It's not in place, right? Like,
Yeah. Because I mean, just here, so here we're building it up in more traditional, or sort of in C, for instance. What you really do is you just straight up say, I need an array of length A plus length B. I need it to be that long. And then you sort of, instead of append, you have an index K, and like it's different syntax and something. And then, you know, you also need, implicitly, we free up some of the memories we get something. Yeah, so merge sort is always going to be N log N, but uses up more memory, and in practice, for other reasons, it's sort of a little bit slower. Still N log N, but you know, correct. Quicksort usually is N log N and sort of simpler and in place. So when everything's working nicely, it's very fast. But every once in a while, if you're not careful, it might go much slower. That's sort of the yeah. And I'm happy to take other questions we have 5 minutes. Or you're free to go, of course. There's been interest, well, let's have like an open forum, just questions for DSA stuff. So there's 5 minutes.
So you said merge sort will always be N log N. Is that even accounting the worst case? Or okay.
And when we say, oh, it's, or when we say this algorithm runs in blah, blah, of N log N, we are saying that in this context of the worst case. And I say that, and they say, well, obviously, quicksort takes O of N log N. Technically, what people say is it's expected to take O of N log N, which is a little confusing because it's expected that the worst case is going to be long. Which sounds a little like, you know, 60% of the time, every time. But it's saying, you know, if you make it nice. Yeah.
well, thanks again.
Oh, it's after the tree. Do you have an array of 1,000,000 elements? But every element is numbered between 0 and 10. There are faster ways of sorting.
Like, can you repeat that?
Oh, if you have like a huge array, but every element of the array is either the number 0, or 1, or 10. Like it's very few possible values.
Mhm.
You can sort that in linear time.
Oh.
Not with these, obviously.
So you say in the first, say you decide to loop, say, how you say in the first 0 to 10, and then comparing it with the next.
I don't quite know. Well, I think we can end the record. This was the teaser for next episode. Not that we might go over this.